So that said 2D yesterday. It shouldn't have, because we didn't do 2D. We just did 1D. Right? Yeah. So sorry. We're still doing 1D part 2. So recall yes. No excuses. Means you got no excuses. To fail? What? Pendulum. And this stuff, I mean, it's like half momentum, it's half energy. Yesterday we talked about kinetic energy, whether kinetic energy is conserved. Total energy is always conserved. Okay, but not necessarily kinetic. It could be transformed to other forms. Momentum is always conserved. So this is half momentum, this is half energy. Now we're going to talk about potential. So again, what chapter do we put this in? Is it momentum chapter, or do I put this in the energy chapter with like work and power and stuff? It's a bit of both. I mean, it's good questions. At the end of it all, you need to know. It's not just, remember in Math 10, I said this is a great question because it incorporates more than one chapter of stuff. Okay? It's not just trigonometry, it's polynomials and trigonometry. Okay? So, we're going to talk more about energy, but it's still momentum. So a pendulum, right here. It's at the side of its travel. And here, if that line is vertical, which it's not, aha, then it's at the bottom of its travel, and no, it doesn't get distorted because it's going so fast, like light speed or something like that, okay? But there's a relationship here between potential and kinetic energy. So kinetic energy, as you know from yesterday, that's the formula. What's the formula again for potential energy? mgh. Yeah. Think about it. If I pick up something over top of your head and I drop it, it may hurt, depending on how much it weighs. And if it is something that has weight, like this hole punch, there's another factor that will determine how much it's going to hurt and whether you regain consciousness or die, and that would be how high do I drop it from, right? Okay, so there's the two factors. Potential. There's lots of energy in that stapler if I put it really high. This guy, if there's no friction here and no air resistance, and I pull it to the side, just like my keys in circular motion, and let it go, it'll continue to go back and forth forever. Total energy is going to be conserved, always. And even if there is friction, total energy is conserved. It's just converted from other forms into what would it be if there was air friction? It would eventually stop. You know this. Well, you hit all those little particles of air and you move them out of the way. When particles move, what happens? Yeah, the KMT theory, right? They move faster, more heat. Okay, so it generates heat. You don't really feel the heat, but that's where it would go. At the top, it goes up and it stops. So what is the kinetic energy at the top? At the sides, not the top, the side. Yeah, right? Because the V is 0, and if that's 0, there's no kinetic energy. But it has some height. Right? From here to here, let's call it h, and this is just some value. I don't know what it is because there's no numbers. That's the most potential it can have because it doesn't go any higher. Then it goes down here and swings to the bottom. If that's the absolute lowest it could possibly go, because this depends on, like, what is my reference for height? At some point it's got to start at 0. This is my zero level, so right here at the bottom there's no potential energy, but it's moving through with some speed v, so it does have some value of kinetic energy. Okay, just y, I don't know what it is, just some number. Okay, so don't freak out. Those aren't other variables, it's just some strange number. Okay, goes to this side, exactly the same thing happens. So if I'm graphing kinetic energy and potential, one of them does that and the other one does exactly opposite. Total energy is just a straight line that doesn't change because total energy is always conserved. Okay, so Ke will go down, okay, to nothing at the sides and then back up. Actually, that we'll call that potential, right? So we start here because graphically that's more visually appealing. We have some potential, it goes to zero right at the bottom, and then it goes to this side, right? And then I don't go backwards in my graph because this would be time. It would just keep going like that again, okay? And continue, 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 perpetual. So, long-winded explanation for what I taught you last year. So example, a 2 kilogram mass swings at the bottom, v is 4 meters a second. That's what I'm talking about, that picture right there. How high does it go? Well, what's the principle under which I solve this question? What's the law? Conservation of energy. Because without that, how can you solve this thing, right? So at the bottom, that's 4 meters a second. How high does it go? That's what I'm trying to find out. I do know 1/2 mv squared because at the bottom I know potential is 0, so I'm not even going to write it. But maybe technically, let's do it. Okay, energy, call it before if you want. This is before, this is after, okay? Before is after, just like thinking of momentum. Okay, but at the bottom, B for bottom, mgh is nothing. And at the top here, it stops. So kinetic is nothing. So from there, I go 1/2 mv squared equals mgh. What am I solving for? H. So something I can cancel here? Yeah. So H is divide by G, V squared over 2G. And V is that. That goes in there. That's 8 divided by 9.8, which I get that. What's the unit? It's a height. It's meters, yeah, because this was meters a second. Okay? Okay? I could give you the height and say what's the speed at the bottom. Same formula, same concept. So that's Physics 11. Let's step it up a bit. Jane, 50 kilograms, runs at Tarzan. Oh, hang on. Runs at 7 meters a second at Tarzan, 90 kilograms. Who is standing at a vine? Gonna sound like circular motion? Could be, could be. The two of them swing off. How high do they go? Jane. Tarzan. Okay, 50 kg, 90 kg. That's before what should I call this? What happens when the two of them, is that like a collision? Sure. Do they stick together? They do. Okay? Now let's say your feet are dangling over there. What do I know? What don't I know? If they're stuck together, I know that's their mass. What don't I know? Yeah. Is this energy? Ah, momentum. Remember, don't forget about that stuff, right? That's the name of this chapter after all. So how high do they go? That's talking this question, but in order to get my speed, which I need to get the height, well, I got to do momentum to get the speed. So 2 questions in one, right? What could be better? So before, let's write that. Momentum to get V, let's call it V after V prime. Then conservation of energy to find the height. So before, total momentum. What's his momentum? Yeah. Because standing at the vine implies he ain't moving. And if there's no velocity, there's no momentum. She has mv, he doesn't. After, we have a combined mass, and I need to know that speed. So 50 times 7 plus nothing is 50 and 90 times v. So the speed they both go off together is, what do I got here? 2.5? Look reasonable? Does to me. I mean, it's got to be less than 7, right? Look okay, Reese? We happy? I'm happy. You're not happy. Why? How do you get what? Conservation of momentum. So momentum of him plus the momentum of her equals the momentum after, which is mv. They stick together, so that's a combined mass, right? Let's solve for their velocity. So that's part 1. Part 2. Here, at the bottom, they have a speed of 2.5. Let's pretend they're a pendulum. Okay? And how high are they going to swing to? I just did this problem. At the bottom, 1/2 mv squared. They have no potential at the bottom. because that's the ground level, right? It's not going to say something like they're on a cliff and they, well, hey, don't quote me, maybe I'll give you that question. Okay, so MGH here is 0, so I'm not going to add it. Whoop, having said that, I almost tried to. At the top, that's what the question says. How high? At the top, there won't be any kinetic because they'll stop at the top. That's what top means. How high do they go? So I do know their mass, but hey, who cares, right? Why put in more numbers than you need? H is 1/2 of E squared divided by G, sorry. And V is 2.5. So, what did I get? 2.5 squared divided by 2, just like divided by 9.8. Let me get a number. 0.32. What is a unit? Meters. Let me stop this and I'll ask you a question.